Welcome. This is Professor Ridge, and today's lesson 6.6, Exponential and Logarithmic Equations. And our first learning objective, use like bases to solve exponential equations. Using the one-to-one property of exponential functions to solve exponential equations. So for any algebraic expressions s and t, and any positive real numbers, or any positive real number b not equal to 1, b to the s equals b to the t, if and only if s equals t. So for instance, if I had 5 to the third power equals 5 to the... Now, for these to be equal, since the exponential function's a one-to-one function, meaning if I put in a number for x, the function, it can only give you one answer, and then vice versa. If I have an answer, there's only one input value to get that answer, right? So basically, for these to be equal, this number has to be 3. So let's say I called it x. And then I could say, all right, the only way these two expressions can be equal, since the bases are equal, then the exponents also have to be equal. So then I can just drop the bases and just say x is equal to 3. Reading backwards here. X is equal to 3. Okay, and then I can solve it that way. So that's a very powerful technique. Now the key is we have to get both sides written with the same base. So we're going to there's a couple ways you can do that, but let's try a couple examples. Okay, example 1, solve an exponential equation with a common base. So solve 2 to the x minus 1 equals 2 to the 2x minus 4. So if we read the technique up here, first step, use the rules of exponents to simplify if necessary, so that the resulting equation has the form b to the s power equals b to the t power. So we want to have the same base on both sides, which we do. So that step's done. There's no work for us to do. Then you're going to use the one-to-one property to set the exponents equal. So again, the only way the left side and the right side could be equal, since they both have the same base, is the exponents have to be equal. Otherwise, these would not give you the same number. So then basically you can drop the bases and say x minus 1 is equal to 2x minus 4. And then from there, you just solve that resulting equation, and then you're done. Okay, so we want to, this is just a linear equation now, so we're going to get all the x's on one side. So 2x minus x is x. And if you want to combine steps, right, I can add 4 to both sides. Negative 1 plus 4 is 3. So x equals 3. And then I'm done. And then if I want to check just to make sure it makes sense, 2 to the 3 minus 1, does that equal 2 to the 2 times 3 minus 4? So 3 minus 1 is 2. 2 squared is 4. And then 2 times 3 is 6. 6 minus 4 is 2. Which is 4. So 4 equals 4. Check. Okay, so our solution is x equals 3. Rewriting equations so all powers have the same base. So again, remember the key is you want to get both sides of the equation with the same base. So you're going to rewrite each side in the equation as a power with a common base. Then once we do that, we can drop those bases and use the one-to-one property that says the exponents have to be equal. So for these two to be equal, the bases are equal, then the exponents have to be equal as well. And then you solve the resulting equation. Now, our first step here, example 2, solve 8 to the x plus 2 equals 16 to the x plus 1. You can see they don't have the same base. So if you recognize that, 8 is a power of 2, I can rewrite 8 as 2 to the third. And 16 is 2 to the fourth. So I can write 16 as 2 to the 4th. Now we have to use some exponent rules. Power to the power as you multiply. So we're going to do 3 times x plus 2. You can distribute that now or we can do it later. It doesn't matter. And then same thing here. Power to power. We multiply. Okay, so now we have both sides of the equation written as a common base of 2. Right? So if the bases are equal, then that tells us that for those two expressions be equal, then the exponents have to be equal as well. So we drop the bases and just say that exponents have to be equal to each other. So 3 times x plus 2 equals 4 times x plus 1. And then our last step, solve this resulting equation for the unknown. So distribute the 3, distribute the 4, get all the x's on one side, the numbers on the other. So let's go ahead and do 2 steps together. So on the left side, we're going to, the 3 x's cancel. 6 minus 4 is 2. And on the right side, 4x minus 3x is 1x. And then the 4's cancel. So we get x equals 2. Okay, if we want to check just to make sure, 8 to the 2 plus 2, does that equal 16 to the 2 plus 1? So 8 to the 4th, does that equal 16 to the 3rd? So let's see, we'll get Desmos or calculator. Okay, so 8 to the 4th equals 4096, and 16 to the 3rd, 4096. So you can see both sides are equal, so it checks out. 4096 on both sides, check. Alright, example 3, solving equations by rewriting roots with fractional exponents to have a common base. So this is 2 to the 5x equals the square root of 2. So if I rewrite remember square root is the same thing as 1/2 power. So if I rewrite that as square root of 2 as 2 to the 1/2 power, now you can see that both sides have the same base. Then we can use our rule, our one-to-one rule for exponents. If the bases match, then the exponents have to match as well for them to be equal. Alright, so then solve the resulting equation. So we're going to divide both sides by 5. So we get x equals 1/10. Okay, and if you want to check, 2 to the 5 times 1/10, that's 5/10. 5/10 reduces to 1/2. 1/2. And then that equals 2 to the 1/2. Remember, for here, when I divide by a fraction, 1/2 divided by 5 is the same thing as 1/2 times, and then I can put this over 1, flip it over, so I get 1/10. We multiply numerators, multiply the denominators. Okay, example 4, solve an equation with positive and negative powers. Okay, so I'm a little confused with this because they're saying positive and negative powers, but do they mean the bases? So the technique then, we got to get the same bases. Well, we can't. There's no way to do it. And then if you think about our exponential function, 3 to the x plus 1, we know it's going to be something, okay, here's just 3 to the x, right? And then we do the plus 1, that shifts it to the left one. So it's going to be something like this, basically, or 3 to the x, something like that. And then y equals, and notice this the output values for 3 to the x, the range is going to be from 0 to infinity. So there's no way this is going to be equal to -2. And if I were to graph, use that technique where we graph y equals 3 to the x plus 1, y equals -2, and look for where they cross, right? You can see that they'll never cross because this one has the horizontal asymptote. It's going to go down to 0 and it'll never get to the negative side. So this one's going to have no solution. Now we're going to learn some other techniques later on of how we would approach this, but if you stop for a second and think about what's the range of this function, the range is from 0 to infinity, so there's no way that a positive number can be equal to a negative number. Okay? Alright, on to the next learning objective. Use logarithms to solve exponential equations. Alright, so the first technique, given an exponential equation in which a common base cannot be found, solve for the unknown. So you're going to apply the logarithm of both sides of the equation. So we're going to use that one-to-one property in reverse for the logarithms. If one of the terms in the equation has base 10, use the common log. If another equation has base 10, use the natural log. This is just their preference. You could use any base at any time. But if it's base 10, using the common log, so if you had something 10 to some power equals whatever, and then you put the log in front of both sides, the common log, we can use that property where these cancel each other out and you just get p by itself. Okay? And the reason they're just giving you two choices for the base is because most calculators just have base 10, the common log, or base e, the natural log. Okay, and then once you do that, you're going to use rules logarithm solve for the unknown. All right, so here we go. So we can't write 5 or 4 as having the same base easily, right? They're going to be decimals. So we'll follow the rule here. Again, I like to use ln anyway because it's one less letter to write. So the natural log, 5x plus 2, equals the natural log of 4x, 4 to the x. Now we're going to use the power rule for logarithms. So bring the power, comes out as multiply in the front, so I got to put that in parentheses. I use a script L for my natural log a lot of times. So again, do that to both sides. I just told you I used a script L, and then I used just a straight one there. Anyway, so now just think of, now this number you can punch into your calculator and get it. So if I were to go to Desmos, ln of 4, so this is what I tell my students all the time. They get stressed out by they see this problem and think, how do I do this? So ln of 5 is just 1.609. Okay, so this equation, and I can move this to the front, 1.609 times x plus 2, and then ln of 4, let me do that real quick, is 1.386. And again, I'm approximating it because ln of 5 is an irrational number, so it has an infinite number of decimal places. Same thing for ln of 4. But if you're struggling with this, you could do what I'm doing here. So we're just going to distribute the 1.609, and then 1.609 times 2 would be 3.218. Okay, this side we don't need to do anything. Okay, now we want to subtract 1.609x from both sides. So we get 3.218 equals, let's see here. 1 point, okay, I'll just figure it out. Okay, that equals negative 0.223. Okay, and x. So now I'm going to divide both sides by that number. So x is about negative 13.811. Now, depending on how many places we wanted, if I wanted accuracy to 3 places, I should have did like 5 or 6 places up here. Okay, so you're going to lose accuracy. So most mathematicians, we don't pick up our calculator until we're all done. Watch, I'm going to do the exact same steps. So this ln5 was the 1.609, and I'm going to distribute it. So that'll be x ln of 5 plus 2 times ln of 5, right, which will be about 3.218. And then this one I don't need to do anything. Typically we write the number, like a whole number or the variable, in front of the ln. That way you don't confuse, like if it's x times ln of 5, right? So we're if I wrote it, if I didn't use the parentheses and I put the x on the back, am I saying 5 times x and then the ln, or am I saying ln of 5 times x? So to avoid that confusion, if I don't want to write parentheses, you write the x in front, because again, multiplication is commutative, so the order doesn't matter. But this number and this number are 2 totally different things. So you want to be careful how you write it. Okay, so now we're going to subtract. We want the x's together on the same side, so we subtract x ln of 5, x ln of 5. So those cancel, and I get 2 ln of 5 equals, and then here what you do is you factor out the x, and then you have the ln of 4 minus the ln of 5. And then this number is the negative 0.233, about, right? If you type that in your calculator, you'll see you get that. And then you're going to divide both sides by this ln of 4 minus ln of 5, which again is the 0.233, the negative 0.233. But the idea is we just write this. This is the exact answer. Here, let me erase. Actually, I can just scroll up a little bit. So now I'm going to pick up my calculator. Here, I'll show you on Desmos. So let's see here. Okay, so I'm going to do, let's see, 2 times ln of 5. I can just type ln 5 divided by, too bad I didn't, here, let's see. See, that's the 3.218, and you can see it would round to 19. So that's why you don't want to, if you want it to be accurate 3 places, you need to round this to more places in the beginning. And then the bottom be ln of 4 minus ln of 5. And you see how this is way off. It's negative 14.425. So this is not even, this is quite a bit off. And it's not that we did anything wrong, it's that we rounded too early. Okay? So you propagate that rounding error and it compounds, and then your answer could be off by quite a bit. So we're off by 0.6 or so. So negative 14.425. But if you're struggling with this notation stuff, I encourage you to go ahead and make it, round it a number, go out a few extra places, like I would say double the number of places you want to be accurate to. So if you want 3 places, go out 6 places if you do it early. Otherwise, just learn how to deal with writing it this way. and you'll be fine. Okay, I want to compare my answer to the way the book presented it in the solution there. So basically, they started the same way we did. Put ln in front, bring the power out in front, and then distribute. So x ln 5 plus 2 ln 5 equals x ln 4. Now here's where they went a little different. They put all the things that have x in it on the left side where I put it on the right side. No big deal. It's not going to change the answer. And then, so they subtracted x ln 4, subtracted 2 ln 5 to end up with this line. Then you factor out the x like we did. And notice since it's on the left side, it's ln 5 minus ln 4 instead of what we had. And then they just use the properties to make this one logarithm. So if you're subtracting, you can divide the numbers inside. And then here we can put the negative 2 up as a power. And remember, a negative power is 1 over 5 squared, which is 25. And then you divide this. And then this is the exact answer. But if you see, if we were to put that into Desmos, so for me, it depends on what I'm doing. If I want the exact answer, then I'll probably do something similar to what they did. But most of the time when you're doing these, you're just going to get an approximate answer, right? So if we do ln of 1 over 25, 1 over 25, oops, divided by ln of 1, no, what do they had? 5 over 4. 5 over 4. And you can see it's the exact same answer that we got. And again, when we round it early, look at how far off again. Oh, I forgot to put my negative in this one. Look how far off that was, right? Quite a bit. So anyway, so if you're going for an exact answer and you want to clean it up a little bit, this is fine. Me personally, I don't. I just leave it the way I had it here. And then I pick up my calculator to get an approximate answer. Okay, equations containing E. So the technique is, given an equation in the form y equals a times e to the kt, solve for t. So divide both sides of the equation by a. So our idea is we want to get e to a power by itself on one side, and then you can apply the natural logarithm to both sides. And then what that does is, remember, the natural log and e to a power, those are inverses, so that's going to cancel out and you'll get that power by itself. And then you can solve for the t by dividing both sides by k. So if you look at the big picture here, we want to get the e to the power. We want to get this part all by itself. So if we have e to a power equals a number, that's the way I think of it, then if I take ln to both sides, the ln and e cancel each other out and you get p all by itself. And then so this power is going to be equal to that. So if the power is k times d and you're solving for t, you just divide by k. Right? So this is the idea of what is built in this technique up here. Okay, so we want to divide both sides by 20 to get the e to the power by itself. 100 divided by 20 is 5. E to the 2t. Now we're going to apply the natural logarithm to both sides. And we're using that 1-to-1 rule basically. And we're using it in reverse this time. So if they have the log with the same base, then the input values have to be the same, and then you can do it vice versa. You can just put log with any base in front of both sides. Okay, this is just a number. ln and e cancel each other, and you just get 2 to the t, or 2t, sorry. ln of 5. And then my last step, I want to solve for t, so divide both sides by 2. And then I'm going to flip this around. So t is equal to the natural log of 5. Again, I like to use a script. ln of 5 divided by 2. Okay, and that's my answer, the exact answer. Now, if I want to approximate it, just type that into Desmos or your scientific calculator. You can tell I like Desmos a lot. ln of 5 and then divided by 2. Now, when you do it, make sure that you see that it's on the calculator that it's ln of 5 divided by 2, or ln of 5 divided by 2, depending on what program you're using or what calculator, because that'll give you a different answer than if it's thinking you meant this. That'll give you a different answer than this, or all right, or this bottom one. So you should get about 0.805. Well, it's 47, so if I do 3 places. Okay, let's look at example 7. Solve an equation. Solving an equation that can be simplified to the form of y equals a e to the kt. So what we're going to do is subtract. So again, the big idea is we want to get this e to a power all by itself. So we're going to subtract the 5 and then divide by 4, and then we can do ln to both sides. Okay, so we subtract 5. So we get 4e to the 2x equals 7. 12 minus 5 is 7. Okay, then I'm going to divide both sides by 4. So those cancel. We get e to the 2x equals 7/4. Now we're going to do ln of both sides. And then ln and e cancel each other, so we just get the 2x. So the input value becomes the output value for this, what we call composition. These are inverses, so we're doing the inverse rule. And again, this is just a number. You can punch it in your calculator and figure out what that number is. And I'm solving for x, so then divide both sides by 2. And x equals ln of 7/4 divided by 2. And again, that's the exact answer. If I want to approximate it, I can punch it in a calculator. So I will do that now. ln of 7/4. So 7/4 divided by 2. I had a problem with it. It took it different than what I wanted. So 0.2798. So if I want to check that, I can do 4 times e to the parenthesis 2 times 0.2798 close parenthesis plus 5, and see that that's close to 12, right? We rounded, so it won't be exactly 12, be close to 12. And you can see when I typed it into Desmos Scientific Calculator, I get 11.99988. So again, because I rounded, so it's not going to be exactly 12, be close to 12. So the exact answer is this expression. Extraneous solutions. Sometimes the methods used to solve an equation introduce an extraneous solution, which is a solution that is correct algebraically but does not satisfy the conditions of the original equation. One such situation arises in solving when the logarithm is taken on both sides of the equation. In such cases, remember that the argument of the logarithm must be positive, right? So our input value, the domain, has to be a positive number. If the number we are evaluating in a logarithmic function is negative, then there is no output value, right? It's undefined, so that could cause some problems. So solving an exponential equation in quadratic form. So e to the 2x minus e to the x equals 56. So on this one, we're going to do, there's this technique. That's a 2. I don't know what happened there. E to the x. I'm going to subtract 56. And I'm going to do what we call a u substitution. So let u equal e to the x. So e to the x is going to be u. And notice what I did, because I was thinking ahead there. 2 times x is the same thing as x times 2, and then using exponent rules I can pull that out as a power. So this be u squared minus u minus 56 equals 0. Now this is a quadratic equation that I can solve from what we've practiced many times earlier in the book. Facts 56 that subtract to 1, so that's 8 and 7. Bigger one's negative, signs are opposite. So we get u minus 8 is equal to 0, or u plus 7 is equal to 0. So we get u equals 8, or u equals negative 7. Now I'm solving for x, so I'm going to do e to the x equals 8, or e to the x equals negative 7. So when I do ln of both sides, ln of 8, ln and e cancel each other, so I get x equals ln of 8. And then that's my answer there. Now on this one, if I do ln of both sides, so I get x equals ln of negative 7, which is not right. That's undefined. That doesn't give me a number, so that's extraneous. We throw it out. So x equals ln of 8. Okay, on to the next learning objective. Use the definition of a logarithm to solve logarithmic equations. Using the definition of a logarithm to solve logarithmic equations. So the idea here then is, this the way I say it is, if you can write it as 1 log equals a number, then we can convert it to its exponential form, basically the definition of logarithm. So b to the c is equal to s. Okay, so we want to get it to 1 log equals a number. So this is the way I think of it. 1 log, oops, I get my pen right. 1 log expression equals a number. And then I'm going to convert to exponential form, which is the definition of a logarithm, basically this statement here. So if I can get this to be 1 logarithm, so we're going to use our properties. So first let's get rid of this minus 3. So we get 2 natural log of x equals 4. Then you got 2 options here. I can divide both sides by 2, or I can take this 2 and bring it up as a power. Let's divide by 2, since 2 goes into 4. If we did it as a power, then we would have a quadratic equation and you'll have an extraneous solution, but I mean, that's no problem. Okay, so now we got 1 log equals a number. And remember, the base for natural log is e. So e to the second power is equal to x. And that's my answer. I'm done. I got x all by itself. So if I want to approximate it, I just do e to the second power and that's 7.389. Okay. Example 10, using algebra before and after using the definition of the natural logarithm. Okay, so again, we can divide by 2 because we want to get 1 log expression equals a number. So here, So now we got the natural log of 6x equals 7/2. Now we got 1 log equals a number, so I convert it. E to the 7/2 is equal to the number inside here, 6x. Okay, and we're solving for x, so now we got to divide both sides by 6. So I divide both sides by 6. And again, this is my exact answer. And if I want to approximate it, I can just type it into a calculator and get an approximate, which you should probably do just to practice using your calculator. Let me tell you. So it's about 5.519. Using a graph to understand the solution to a logarithmic equation, solve ln of x equals 3. So another way we can do it, again, is using graphs. So if we were to get Desmos graphing calculator, and remember, we're going to put in the left side for one equation. So we do y equals ln of x, and then we do y equals 3, and we get both graphs. So let's see here, and then we're going to look for where they intersect, and you just click, and remember the x coordinate where they intersect is the solution to the original problem. So 20.086 if we want to round to 3 places. Okay, so x is about 20.086, right? So again, we do the log function. Ln of x is something like this, and then y equals 3, and we look for that intersection point, and it was at 20.086 about. Now, of course, we wanted to solve this algebraically, right? We got the log equals a number, so we convert it to the exponential form. E to the 3 is equal to x. And if you type in your calculator e to the 3rd power, you're going to get this number, 20.0855, on forever. Okay, the next learning objective, use the one-to-one property of logarithms to solve logarithmic equations. Okay, so using the one-to-one property of logarithms to solve logarithmic equations, for any algebraic expressions s and t and any positive real number b, where b is not equal to 1, log base b of s equals log base b of t, if and only if s equals t. So again, and then note, when solving an equation involving logarithms, always check to see if the answer is correct or if it hasn't, or if it's an extraneous solution. So again, you got to remember, because of the domain issues, s has to be a positive number. So you got to check to make sure you don't get a solution to your related equation that is not a solution to the original problem. So you always have to check that. Okay, so it's just like we did with the having the same the exponent one, where we said, hey, if base to some power equals base to some power, that can only be true if s and t are equal. Same thing with logarithms, right? So the idea is, if I can get one log on both sides of the equation and nothing else, just one logarithm, and they have the same base, you can drop the logarithm part and say the arguments s and t have to be equal. So that's the technique. Let's try one. Okay, so use rules of logarithms to combine like terms if necessary. So the resulting equation has the form, again, you want 1 log equals 1 log expression on both sides with the same base. That's the way I think of it. Okay, then you're going to invoke this one-to-one property of logarithms, so then the input values have to be the same. So s has to equal t, and then you solve that resulting equation. So here it's all ready to go. We got 1 natural log equals 1 natural log. So the only way these two expressions can be equal to each other is if the arguments, the input values, are equal to each other. So so basically there's no work to do for step 1. Step 2, okay, they're the same base, so we drop the logarithm part and just say x squared has to equal to 2x plus 3. Now I solve this resulting equation. So this is a quadratic equation, which means I need to get it equal to 0. Factor it if I can factor it. If not, use quadratic formula. So let's see, -3, +1. Factor 3, this subtract to 2. So 3 and 1 is my only choice. And it works. So then set each of these equal to 0. Subtract 1, so x equals -1. Now we're going to check for any extraneous solutions, make sure these are in fact the solution. So ln of 3 squared, does that equal ln of 2 times 2 plus 3? So we get ln of 9. Does that equal ln of 4? Oh, it was 2 times 3, sorry. I was going to say no, it doesn't. 2 times 3 is 6, plus 3 is 9. So yeah, that one works. So that's x equals 3. Now check x equals -1. So ln of -1 squared, squared, does that equal ln of 2 times -1 plus 3? So -1 squared is 1, and then 2 times -1 is 2, -2, plus 3 is 1. So they both work. So we have two solutions, 3 and -1. Alright, the last learning objective, solve applied problems involving exponential and logarithmic equations. Example 13, using the formula for radioactive decay to find the quantity of a substance. How long will it take for 10% of a 1,000 gram sample of uranium-235 to decay? So I need the chart for the substance up here. So basically you can read the text up to this spot here to kind of see where how they derive that formula. I do it a little differently, but I'll go with the way the book's doing it here. So we got this half-life formula. This is the radioactive decay formula, is just basically your amount as a function of time equals a sub 0, which is your initial amount, e to the RT. Now if r is a positive number, this is exponential growth, and if r is a negative number, which would be decay, that would be exponential decay. And so using this formula, you can see how they're derived and to get to this half-life formula. So T is your time period over which substance is studied. The capital T is the half-life of the substance. And A sub 0 is the initial amount, or you can read this A naught, N-A-U-G-H-T. Okay, so A naught or A sub 0. And then A of T is the amount of substance present after time T. So here we go. So we want uranium-235, the half-life is, well, 703 billion, no, that's million, 703,800,000 years. So we're going to say, all right, how long will it take? 10%, let's just start out with the formula. A of T equals the initial amount, 1,000 grams. We do 1/2 T over capital T. Capital T for uranium is that big old giant number, 703,800,000. Okay, and we want to, how long will it take for 10% of the gram sample to decay? So 10% of that to decay, that means we're going to be left with 900 grams, right? So if you do 10% of that, it'd be 100, and then subtract it. So we'd be left with 900. So if 10% decays, you got 90% left. How about that? Maybe that makes more sense to you. Okay, so we want, now we're going to solve this, so we want to get the 1/2 to the power by itself. So first we divide by 1,000. So that cancels, and we get 1/2 to the T over 703,800. 703,800,000, and then that's going to be 0.9. Now we're going to ln both sides, or you know what? Yeah, let's ln both sides. So ln 0.9 equals ln of 1/2 to the T over that number. I should have just left it capital T, and then we could have done it later. Now I'm going to bring this out in front. So ln of 0.9 equals, I'm going to write capital T because I'm tired of writing that big old giant number. ln of 1/2. Okay, I'm going to divide both sides by the ln 1/2 because I'm solving for T. So I'm going to do ln of 0.9 divided by ln of 1/2, which is 0.5. I'm going to do 0.5. And then I have to times it by T. So times T. Now I can just get out my calculator and punch this all in. So let's see here. We can just use so let's see here. We're going to do ln, so ln of 0.9. Okay, divided by ln, oh, they didn't like the 0.9 like this, 0.9, ln of 0.5, and then times T, which is the half-life, which is 703,800,000, which is, so it's going to take, let's see, 306 million years. So T is about 106,979,777. Okay, so 107 million years, basically. Okay, and that brings us to the end of the lesson. So again, practice, practice, practice. go to the end of the exercise or to the section and do the exercise set for that section. Again, all the odds. If you have time, do some of the evens. Do as many as you can. All right, have a great day, and I'll see you next time.